Welcome to This Explainer. Today, we're unpacking a fascinating and, honestly, often invisible connection that sits right at the intersection of modern civilization. We're looking at the link between generating the electricity we all use every single day and managing our increasingly fragile global water supplies. We're talking about billions of gallons a day here, so let's just dive right into this.
I want you to think for a second about the visceral, physical reality of what actually happens behind the scenes when you flip a light switch. We usually picture power lines, humming generators, maybe a spinning wind turbine or a massive coal furnace, but there is a hidden, massive ingredient in that recipe. So, what does keeping the lights on actually have to do with global water shortages? Well, as it turns out, absolutely everything. The power grid and the water grid, they're locked in this high-stakes stance.
Section 1. The Water Energy Nexus. To really grasp this nexus, we have to look at how our power is actually generated. See, the vast majority of our electricity comes from thermoelectric power plants. We're talking coal, nuclear, natural gas. And the vulnerable lifeblood of these facilities, the very thing that keeps them from literally melting down, is massive, and I mean massive quantities of water for cooling. In fact, if you look at the Sustainability Accounting Standards Board, or SASB, they say it plainly: electricity generation is one of the most water-intensive industries in the world. In terms of sheer water withdrawals, it actually rivals agriculture. Without a steady, massive flow of water, a thermoelectric power plant just can't operate. It's a dependency that's worked out totally fine for decades, but well, the ground rules are shifting rapidly now. Section 2. The Scarcity Threat. We're transitioning into an era where we simply can't take unlimited, cheap water for granted anymore. Global water supplies are tightening up. We've got increasing consumption colliding with reduced supplies from climate change, and that's bringing more frequent and intense droughts. This poses a fundamental, structural threat to power generation. Let's break down what these water scarcity risks actually look like on the ground. First off, power plants are increasingly finding themselves in direct competition with agriculture and everyday community needs. And when water gets tight, tensions rise. This can lead to the sheer inability to operate plants at full capacity, which introduces a massive financial threat: the risk of creating stranded assets. Just imagine a multi-billion-dollar power plant that becomes financially worthless just because it literally doesn't have the water to run. Add to that the increasing regulatory constraints on how much water a plant is legally allowed to withdraw, plus intense scrutiny on biodiversity impacts, like fish and aquatic life being harmed by these massive intakes. Section 3. Withdrawals versus consumption. Because this scarcity risk is just so massive, investors and regulators obviously need a way to measure it. The SASB standard provides a very specific metric for this, IFU 140A.1, which helps track exactly how much water these utilities are interacting with. But to fully understand it, we need to clear up some vital industry jargon. The crucial point here is understanding the stark difference between withdrawing water and actually consuming it. So water withdrawn is the total amount of water taken from any source, whether that's a river, a lake, groundwater, or a municipal supply. But water consumed is very different. This is water that's actually lost to the local environment. It's the water that evaporates during the cooling process, or water that gets discharged into a completely different catchment area or into the sea. Basically, it means it never returns to its original source. So a power plant might withdraw 1 billion gallons, but only consume a fraction of that through evaporation. But make no mistake, both metrics matter deeply depending on the local ecosystem. But context is absolutely everything here. Withdrawing 1 million gallons in a rainforest is obviously very different from withdrawing 1 million gallons in a desert, right? Under this standard, companies are required to analyze all their operations using tools like the World Resources Institute's Aqueduct tool. They actually have to disclose the percentage of their water withdrawn and consumed in specific danger zones. For example, a high baseline water stress means 40 to 80% of available water is already spoken for, while extremely high means over 80% is claimed. If a utility operates heavily in these red zones, their financial and operational risks just go straight through the roof. Section 4. Navigating compliance risks. So, water risk isn't just a supply issue, it's a strict regulatory and environmental compliance issue. What goes into the plant must eventually come out, and believe me, regulators are watching very closely. When a power plant discharges water back into a river or a lake, it can't just dump it however it wants. Companies must track and report any formal enforcement actions taken against them. This includes stuff like violating statutory permits, failing to meet pre-treatment requirements, or exceeding total maximum daily load limits for pollutants. It also includes temperature controls. Get this, if a nuclear or coal plant discharges water that is too hot, it can completely devastate local aquatic ecosystems. Violating these standards results in severe regulatory penalties, massive compliance costs, and some serious reputational damage. To make this a bit more concrete, the SASB framework uses metric IFEU 140A.2. This specifically isolates the exact number of incidents of noncompliance associated with water quality permits, standards, and regulations. It takes this abstract concept of environmental risk and makes it feel incredibly weighty and quantifiable. It literally forces a utility to put a hard number on how many times they faced formal enforcement actions. For an investor, or even just an informed consumer, a high number here is a giant red flag. It's a flashing indicator of poor management and looming financial liabilities.
Section 5. Strategies for mitigation.
Okay, so how do we actually fix this? Power generators aren't exactly sitting ducks here. They have targeted strategies they can use to survive, maintain their financial viability, and protect the environment. These are captured under metric IFEU 140A3. Let's walk through some of these essential mitigation steps. Number 1. Efficiency efforts. Think upgrading to water recycling or closed-loop cooling systems. Instead of constantly pulling fresh water from a river, they reuse the same water over and over, which drastically reduces withdrawals. Number 2. Process innovations to reduce aquatic impingements and entrainments, which honestly is just a very technical way of saying they install better screens and intake systems so fish and marine life don't accidentally get sucked into the plant's machinery. And number 3, proactively analyzing their long-term exposure using advanced mapping technologies like the WWF water risk filter to actually guide where they site new plants.
But, and I think this is a truly fascinating part of the reporting standard, companies also have to transparently discuss their life cycle trade-offs, because there is no free lunch in energy generation. Sometimes fixing a water problem just creates a brand new issue. For example, switching a plant to a dry cooling system uses almost zero water, which sounds great, right? But actually, it's a trade-off. Dry cooling is often less energy efficient, meaning the plant has to burn more fossil fuels, which then increases greenhouse gas emissions. Or it might require significantly more land use. So utilities have to publicly weigh these trade-offs and explain exactly why they chose a specific practice despite the impacts on other environmental areas.
Which brings us to our final thought. We've explored the hidden lifeblood of our power grid, the severe risks of scarcity and compliance, and the really complex trade-offs required to keep everything running. The true cost of our energy goes far, far beyond that dollar amount on our monthly bill. It's intrinsically tied to the water flowing through our local ecosystems. So I'll leave you with this question to investigate. Is your local utility actually prepared for the next great drought? Thank you for joining me for this explainer, and I highly encourage you to look a little deeper into where your own power and water comes from.